Take a system built on continuous, unpredictable randomization and map it onto a strictly ordered sequence of integers. The friction between continuous probability and discrete geometry usually requires us to rely on approximations to make sense of the results. But look at this identity. If you take a slice of the Fibonacci sequence, approximations here, no rounding errors are used to make the math look cleaner. This is a rigorous, exact algebraic equality. To understand why this happens, we have to look at the variables. Capital U represents a continuous, uniform distribution, a probability model where every value between 0 and 1 has an equal chance of occurring. That random value is scaled by the irrational exponent phi squared, and then passed through a floor function. A floor function is a mathematical operation that takes a real number and rounds it strictly down to the nearest integer, forcing the result to be a valid sequence index. Scaling a continuous random variable by an irrational number like the square of the golden ratio usually results in a chaotic scatter of data. Instead, it yields a perfect closed-form divisor pulled straight from a discrete sequence. The mechanism that makes this possible is an additive window. Certain linear recurrences possess a specific internal structure that forces this collapse to happen. By mapping the strict boundaries of these sequences, we can identify exactly which algebraic constants are permitted to divide them and which the math entirely rejects. We begin by establishing our probability space. The variable u is uniformly distributed, meaning any value starting at exactly 0 and approaching 1 is equally likely to be selected. Next, we introduce a scaling parameter, lambda. We place a limit on lambda. It must fall strictly between an integer m and the next integer m plus 1. This 1D number line shows what happens when we multiply our uniform distribution by lambda. The probability interval stretches along the axis, anchoring at 0 and extending to our new parameter limit, stopping before it reaches m plus 1. The floor function now acts on this stretched interval. Because it rounds every value down to the nearest integer, it slices the continuous line into distinct, discrete integer buckets. For every full integer bucket from 0 up to m minus 1, the probability of our randomized index landing inside is exactly 1 divided by lambda. But the final bucket at position m operates under a different boundary condition. Because lambda falls strictly between m and m plus 1, this bucket only captures the fractional remainder of our stretched continuous line. The precise probability of landing in this final remainder bucket is exactly lambda minus m divided by lambda. The floor mapping functions as a mathematical prism. It accepts continuous uncertainty as an input and outputs uniform discrete probabilities, accompanied by one specific remainder. With our discrete probability distributions established, we can calculate the expected value for a randomized variable generated by this process. We apply this to an order m additive window. This is a sequence where the final term is defined as the exact sum of the m terms that immediately precede it. This is the raw formula for our expected value. It sums every term in our sequence, multiplied by their respective probabilities of occurring. If we isolate the summation portion of this equation, we are looking at the combined weight of the first m terms of the sequence. Under the rule of an additive window, this entire summation must perfectly equal the final sequence term, am.
We substitute am into the equation, which allows us to factor the terms. By grouping the am components together, the fractions combine. The math reduces to a final expectation formula that depends entirely on two variables, the final sequence term and our scaling parameter. The additive constraint erases the individual influence of every early term in the sequence, leaving a clean one-parameter relationship. Rather than just calculating a random expectation, we can use this relationship to target a specific divisor, which we will call capital C. This graph plots the parameterization function from our collapsed equation. We map it across its active domain on the x-axis, from m to m plus 1. Taking the mathematical derivative of this function proves that it is strictly decreasing across this entire interval. Because of this slope, the y-axis outputs map strictly onto a specific range, bounded exactly between m plus 1 over 2 and m. This creates a bijection, a mathematical mapping where every output is paired with exactly one unique input. This property guarantees that every valid divisor C in our range has exactly one unique scaling parameter lambda. Because the mapping is 1-to-1, we can algebraically invert the relationship, solving the equation for lambda instead of the divisor. This produces the exact inverse formula, lambda equals c times m minus 1 divided by c minus 1. This inverse relationship ensures that for every valid divisor c, there is a single computable lambda that produces that exact result. It provides a direct pathway from a discrete target to a continuous scaling factor. We can now field test this newly derived inverse formula using the Fibonacci sequence. The Fibonacci sequence is an order 2 recurrence, where each term is the sum of the two before it. This fixes our m value at exactly 2. Plugging m equals 2 into our limits dictates a strict admissible interval for valid divisors, locking them between 1.5 and 2.0. The golden ratio, denoted by phi, has a numerical value of roughly 1.618. Because phi falls safely inside these bounds, it is a mathematically valid target divisor for randomized Fibonacci slices. Plugging phi into our inverse formula neatly reduces the algebra, yielding exactly lambda equals phi squared. The identity from the beginning is an inevitable consequence of the golden ratio natively residing inside the exact topological limits of order 2 probability. To test the strictness of this model, we apply it to the Tribonacci sequence. This relies on an order 3 recurrence, shifting our m value to 3. This shifted number line establishes the new admissible zone. The structural change strictly bounds all valid target divisors between the integers 2 and 3.
For an order 3 sequence, a natural target candidate is the Tribonacci constant, alpha, which carries a value of approximately 1.839. Plotting the Tribonacci constant against our new boundaries creates a stark mathematical conflict. The model rejects the sequence's fundamental constant. Alpha's value of 1.839 falls short of the interval limits, making it invalid. However, adding 1 to alpha gives 2.839. This pulls the constant into the 2 to 3 interval, validating it as a target. Using this admissible divisor in the inverse formula yields a specific scaling parameter, 2 times the quantity alpha plus 1, all divided by alpha. The admissible interval is a merciless mathematical filter. It reveals a hidden structural law, dictating precisely which constants possess the geometric properties required to bridge the gap between continuous randomness and discrete reality.